Here is exercise 6 of chapter 4. The idea is to repeat the same procedure as in the previous exercise. So using the dot product to implement convolution. And now we are just using a different kernel and a different signal. And in particular, the kernel is going to be something that looks like a Gaussian. You can already see from these numbers it's going to come up and to a peak and then come down. You can also see it's symmetric around the center. So it looks like a bell-shaped curve. And then the signal, instead of being a plateau, is just going to be a bunch of random numbers. Okay, so here is the kernel. Here's the signal. Again, I'm drawing lines between them, which is probably not really appropriate. But anyway, it's just a bunch of random numbers. And what you can see, I'll zoom in here. What you can see is that, so the original data vector is in black, and then the gray dashed line is the result of convolution, or this feature map of this sliding time series of dot products between the kernel, which is this Gaussian, and the data. And it looks smooth, right? It's you can really see that. Maybe that's zoomed in a little too much. You can really see it here. So the result is like the original signal, but it's smoothed out. And the reason why it's a smoothed version is that this kernel is like taking a weighted sum, so a linear weighted combination of the elements in the time series signal. And the weights are defined such that the center point is weighted the most, and the further away you get from the center, the less weight, the less of the contribution. Okay, so similar concept using dot products for feature detection and just different signals and different kernels. Here is where I create the kernel. You can see I call it a sort of kind of Gaussian. That's because this is roughly a Gaussian shape. It's a good approximation of a Gaussian, but I'm not using the formal Gaussian formula to create this kernel. So therefore, it wouldn't be really technically accurate to call this a Gaussian kernel. It's a sort of kind of Gaussian. Okay, here I'm dividing by the sum. This is basically just setting the integral of the kernel to be 1. This is a normalization factor. You can try rerunning the code without this normalization. So you can just comment out this line, and you'll see it doesn't change the fundamental result. We still get a smooth result. It's just going to be higher. It just adds this linear offset to the signal. Okay, so this is just a little bit of housekeeping here, because we need to set the dot product to go from each center point minus in time to plus in time. So therefore, we need to know how long this kernel is, how many points are in the kernel, in order to appropriately index the signal inside the for loop. Okay, let's see. So this first cell just creates or visualizes the kernel and the time series signal. And then, well, here I'm making a copy because I want to plot the original signal on top. So I don't want to just overwrite the original time series variable. Okay, and then, the setup may look slightly different variable names compared to the previous exercise. But you can see that the mechanism, the linear algebra operation, is identical. We're computing the dot product between the kernel and little snippets of the time series, and obviously each snippet of the time series needs to be the same length as the length of the kernel, so it needs to have the same dimensionality, the same number of elements. Otherwise, the dot product is not defined. And that is the reason why I had to do this extra housekeeping stuff, just to figure out in code what is the appropriate piece of this time series signal to grab before time t and after time t. Okay, and then the rest of this is just code to implement the plotting. So here again, you see that the result of convolution is a smoothed version of the time series signal.